Welcome back, nerds, to the exciting conclusion of whatever the heck this was. Was it section 2.1? Yeah, 2.1. All right. We, on Friday, practiced solving absolute value equations, and what we said was base case scenario, stuff on the inside happened to be a positive number, so absolute values did nothing. Worst case scenario, stuff on the inside was actually a negative number, and the absolute values would have hidden that from us. Solved them both, and as we saw in this very last example, occasionally some things that are not allowed to happen do happen. But I can't remember if we actually talked about why we get these kinds of occurrences, where the math gets us to bad answers, so to speak. The reason why that happens is because absolute value graphs have a very restricted size and shape. Like they can only point either both ends up or both ends down. But the moment you do this, you've literally set two straight lines equal to each other. And as long as two straight lines don't have the same slope, they will intersect. So just understand that even though they're different, they are both straight lines. I mean, if you think about it, every absolute value graph can actually be split apart into two different straight lines. And, don't look at that. Oh, you can't even see it on the camera anyway. You know what? I better use my graphing calculator. That way it's on screen. Not that stuff, though. We do the absolute value graph. Math, number, absolute value of x, zoom, 6. There. So this is the absolute value of x on our graphing calculators. But realize that side is the line y equals negative x. And realize that side is the line y equals positive x. So if we were to write this as two separate things, both a positive case and a negative case, what we're actually allowing the graph to do is continue this path and continue this path. So occasionally they'll give us nonsense, and occasionally they'll give us intersections that never actually occurred because the graph didn't exist where the intersection tried to occur. There we go. And you'll see that happen in this example right here, which is another reason why we always check our answers. I am going to apologize. We're going to have to check these answers and deal with plugging numbers in and following a lot of mathematics, but it's still doable. You're all really smart. I taught you one way of doing things that I said will always work. And I told you that just because it's going to always work doesn't mean it's always the most efficient. This is one of those times where, honestly, I would have done it differently. But it's only because I have a ton of experience showing me what kind of things I can get away with. And I would strongly advise against taking any shortcuts unless you know 100% that you're not going to goof up the algebra. So in my notes, I'm not going to be taking any of the shortcuts that I know I could take. Instead, I'm going to do exactly what I taught you, and that is isolate the absolute value bars. They're almost alone. That fraction on front, that's got to go if you use my method. Yes, sir? Crud. I wrote +7, didn't I? Well, at least we caught it early. Thank you. Yes, 7 + 4 is definitely 11. Yes. Okay, anyway. This is one of those times where, honestly, I wouldn't move the 2/3. But I want you to stick to one method that you're really good at. So if you think you can pull it off without moving the 2/3, cool. I'm just not a fan of going against what I already said, and that is I'm going to teach one way. Plus, this gives us the opportunity to talk about how to get rid of fractions. You guys know how to make that 2/3 go away? Anybody? Multiply by 3/2. Yeah, man. So if we multiply both sides, it's by 3/2, which is called multiplying by a reciprocal. Then on the left side, all that's left is the absolute value bars. Absolute value of 3x plus 6. On the right side, though, okay. Remember that 3 here is 3/1. So when you multiply 3/2 to 3/1, you multiply the 3's on top. That's how I'm going to get the 9. And you multiply the 2 and the 1 to get 2, and there's my x. And the same thing happens with this 11 which is technically 11 over 1, that gives us a 33 over 2. Once again, is this how I would have done the question? No. There's a much faster, easier way to do it. I can do it because I've practiced a lot. This is the point where I taught you to write out your two separate equations. You've got your best case scenario and your worst case scenario. Best case scenario is the absolute value bars weren't going to do anything because 3x plus 6 was already going to be positive. Well, if that's what's happening, they're not needed to be written. But the worst case scenario is, and I'm going to have to get skinny math over here, is what if 3x plus 6 was negative? What if I could have said 3x plus 6 wrapped in a set of parentheses with a negative 1 in front of them was equal to 9 over 2x plus 33 over 2. And we're going to solve these two things separate from one another. Let's be real. Most of you don't like fractions, right? So because these things have the same denominator, I want to get rid of the fractions again. Multiply by 2 is going to get rid of all the fractions. But Mr. M, we just moved the 2. I'm aware. That's because that's one of those things that you could have gotten away with not moving if you were really, really comfortable with it. When we distribute here, what it's going to give me, though, is 6x plus 12 equals. Now here, when I distribute the 2 and the over 2 cancel, just leaving me the 9 and the x. And the same thing happens here with the 2 and the over 2, just leaving behind a 33. And we just solve for x the way we know to solve for x. Bring all your x's to one side. I would rather not goof around with negative x's if I can avoid it. So I'm going to subtract 6x from both sides. I mean, sometimes it's unavoidable and you don't have a choice, but I have a choice right now. I'm going to divide both sides by 33. Excuse me. Subtract 33 from both sides. Oh my gosh, I even wrote division after I said I was going to subtract. Minus sign, big 33. There we go. Minus 33. It's very hard to write and think and talk all at the same time. I imagine that's how drum players feel. Like when you have the big drum kit and you need both your hands to be doing something different from both your feet, or maybe even piano players. It's pretty rough.
It becomes muscle memory.
Muscle memory?
Yeah.
So what's my excuse? My brain muscle not strong enough?
No. Never said that. You need some practice.
I need more practice. There it is. Practice makes perfect, right? It's only the third time today I've taught this. It's okay. I just make new mistakes in each iteration of the notes. No big deal.
3 more times and you'll be perfect.
Is that what it takes?
Yep.
3 more. Okay. Giving me x equals negative 7. That was a lot of effort, but we did get a result. Let's go ahead and solve the other one, and then we'll check our answers. Cool beans? Yes, ma'am. Where did I get the 2? This 2. Because I was just multiplying by the least common denominator. Because both these say divide by 2. So multiply by 2 is the inverse of that, and they'll just cancel out. For example, if one of these was a 4 and the other was a 5, I would have multiplied by 20. Because the least common multiple of 4 and 5 is 20. And what that would have done is it would have canceled both my fractions after some reducing. Because it's a little crowded over here, I'm going to switch colors. Negative 3x minus 6 equals 9 halves x plus 33 halves. And just like we did before, we don't want to have to deal with the divide by 2, so we're going to multiply both sides by that 2. Hey. We're going to distribute that 2 across the entire equation that we see down here. So we're canceling divide by 2 is what they multiply by 2. This math is going to have to get really skinny because this gigantic 33 here. Negative 6x minus 12. So it's almost the same thing. Equals 9x plus 33. Again, if I can, I like to avoid my negative x's. So I'll add 6x to this side. Got really cramped. I'm sorry. Subtract 33. Divide by 5. Divide 15, excuse me. Gives us our second solution of x equals -3. Now we do have to check both these solutions, especially since we were dealing with the absolute value equation that had x's on the inside and x's on the outside. Those are big time no-nos. You got to watch out for that because there's plenty of times where the math gives us a bad solution or two. 100% possible because the moment I stopped writing my absolute value bars, I introduced possibilities that weren't there before. So let's check the -7. A lot of verbal math here, but 3 times -7 is -21. -21 plus 6 is -15. Absolute value of that is +15. Times 2, 30, divide by 3, 10. 10 minus 4 is 6. Okay, this is 6 on the left side when I use this digit. Let's try it over here. 3 times -7 is -21, and -21 plus 7 is -14. So when I try to use x equals -7, I get 6 equals -14, which is clearly not true. No. So what happened? This is called an extraneous solution. And extraneous solutions aren't actually solutions. It only worked because I got rid of the absolute value bars. We also have to test the -3 though to make sure it works. 3 times -3 is -9. -9 plus 6 is -3. The absolute value of that is +3. 2/3 of 3 is 2, and 2 minus 4 is -2. -3 times +3 is -9, and -9 plus 7 is -2. So I got -2 equals -2 when I used x equals -3. So this is a true answer. This was so much cooler on Desmos, but I wanted to make it to the video. So I'm going to type the equation, 2/3 math number absolute 3x plus 6 minus 4. And we're going to set that equal to 3x plus 7. V-shaped graph. And then 3x plus 7 is linear. And I'd like you to see that those two graphs encounter each other one time right there at x equals -3rd. And look at this blue line's slope compared to this red line's slope. Over here, they're both positive slopes, but the red line has a slope of +3, whereas the blue line has a slope of +2, which means the red one is going to get further and further and further away from the blue one the further to the right I go. So why was the math able to give me two solutions? Because here, I set my stuff equal to a linear equation. 3x plus 6 was equal to 9/2 x plus 33/2, which is essentially this line right here. And if we let it keep going down, eventually there's another intersection point down here. So the absolute value graph made this piece of the graph, if you want to think of it like this, snap and rotate up to here. That's what the absolute value bars did. And that's actually the only reason why I have a solution, is because the negative sign encounters this line. Whereas this side, if it had kept going, eventually would have encountered down here. Does that make sense? It looks better on Desmos. I can actually like make the straight line come in and out of existence. What is that line? Y equals, it looks like y equals 2x. Is it? Yeah, there you go. So this is the line y equals 2x right here. And if I zoom out a little bit further, is that the same zoom? That's the same zoom. Did I not just hit zoom out? Why did it do that? It's not working. I'm hitting zoom out. It's not working. Totally wasting our time. Do as I say, calculator. Now it didn't have a choice. Much faster on Desmos. Anyway, the y equals 2x, there you go. So this intersection down here, this happened at x equals -7. But our blue graph didn't exist there. But it's what happens if you take this piece of the absolute value graph and snap it and allow it to be a continuation of this side. So anyway, that's how extraneous solutions occur, because the absolute value bars make something V-shaped instead of making it two straight lines that go on forever in both directions. That's how they occur. All right. Now, we don't need a lot of space because we're not going to solve this one. Instead, we're just going to talk about how we would solve it. You've seen positive and negative cases now. What do you think happens if we have to do absolute value equals absolute value? You could take a guess if you want. Worst case scenario is you're wrong, right? No? You moved your hand. No? Either one of you? Okay. Well, any ideas what we could do? Thoughts? Okay. Parker?
You put the equation in parentheses and then do like the -1 and then like the best case and worst case.
So best case and worst case. And how many cases do you think that sets up?
4.
It looks like it sets up 4, right? And honestly, it could. It could set up 4 cases where this one's plus or minus or this one's plus or minus. The good news is, if you do that mathematically, 2 of them end up being identical to one another, which is really nice. So all we have to do actually, thank goodness, right? Because that's not a lot of space, and I have some of these for you in your homework. All you have to do is just pretend the absolute value bars were only on one side. That's all you have to do. So it's really not bad. So what we're going to do is we're just going to drop the bars off of one side. Then we'll set up the 2 cases. And after we solve, we will check for extraneous. We're always checking our solutions to make sure they work. And if it was me, just because, I would get rid of the bars on the right side. Why? I don't know. I just like my bars on the left, I guess. I don't know. So this is what I would have done. I would have set that up and solved. Well, that seems oddly familiar. Ta-da. But yeah. So you know how up above we only had one solution at x equals -2? And that was from Friday's notes? Watch what happens if I do them both on the grapher. Math number absolute x minus 1. Math number absolute x plus 5. Zoom 6. We get 2 V-shaped graphs. But as you can see, they have the same slope over here and the same slope over here, so they'll never intersect each other ever again. This happens the one time at x equals -2. Yeah, which is really nice. So you could set up all 4 cases, but 2 of them end up being identical anyway, so you just don't worry about them. On to bigger and better. What about absolute value inequalities? You don't need to graph these things. I'm showing you the graph. That way we could actually understand what's happening graphically when we set up an inequality. When we look at this, we could just do the algebra and solve. But I need you to understand what it's actually asking you to do. It literally says, when would these absolute values set up, when would its values be under the number 5? Or even better yet, when would this thing's V-shaped graph be underneath this horizontal line? So here's the picture of it. And I'm hoping that we can all see which part of the V-shaped graph is underneath the line. y equals 5. Looks to me like the answer is between -4 and +6. Not inclusive, because when the V-shaped graph is on the line y equals 5, you're getting 5 is less than 5, which is not a true statement. So not including those two numbers. But I don't expect you to graph them to solve these things. I just want you to see that that's what's happening graphically. It's when the V-shaped graph is literally underneath this line. Yes?
Why is there a negative? Why is there a negative 4 instead of -5?
Right here?
Oh. I thought it was somewhere else. My bad.
No worries. Let's solve it algebraically. Set up the exact same way. Best case, worst case. Best case scenario, x minus 1 was already a positive number, not even sweating. But what if x minus 1 wasn't a positive number? I think it's pretty obvious on this one. You just add 1. And you're going to get that x is less than 6. Which is good because, look, check it out. Less than 6. That's going to give us this piece right here. And then this one. When you distribute this -1, you get negative x plus 1 less than 5. We'll subtract 1. Negative x less than 4. And we'll divide by -1. And who remembers what's going to happen when I do that? Inequality. Yep. We have to flip that inequality over. X is greater than -4. I am not a fan of telling students rules without showing them why these rules were put in place. And I'm going to be real with you. This whole flipping the inequality over because it's a negative, why? Why would you do that? I mean, were you ever given an explanation as to why that happens? No, you weren't. You were just told, hey, here's something we do. Don't screw it up. Are you kidding me? Let me show you why it's true. Let me go back to this statement right here. Negative x is less than 4. Someone's at the door if you don't mind. Negative x is less than 4. I don't want to do any sign flipping or anything like that. So what I am going to do instead is pause my video because I have an intruder. So anyway, I don't want to do any sign switching or any kind of rule that I just have to remember to do. Okay? So let's try to get this answer set without doing any kind of weird rules that we don't know why we're doing them. I was telling you earlier I like my x's to be positive. So I'm going to go ahead and add x to both sides. But I am trying to get x by itself. The statement says that -4 is less than x. But if I wanted to read it backwards, if I said -4 was smaller than your x's, then you would say your x's are greater than the -4. You see, dividing by -1, flipping the sign over, is a shortcut. It's making it so that way you don't have to move everything from one side to the other and vice versa. It's that way you don't have to move all this stuff to the right and all this stuff to the left. When the net result is, oh, divide by -1, flip that sign over. But this is why that happens. So that you know why it's occurring, if you're concerned that you're going to forget to do that, by all means, just add the x's to the other side so that they're positive. And then get them alone. And you'll never have to worry about switching any signs again. That's why, folks. Now, if I was going to graph this answer set, numbers that are less than 6, numbers that are greater than -4, here's the thing. There are numbers that satisfy both of those conditions on the number line. Whoops, just threw my pen. because every number in between those two is greater than -4 and less than 6. And that is how we would write that, from -4 to 6 without brackets. Ta-da! Not bad, right? Not bad at all. And you could either remember to do the sign switch, or just get your x's positive by moving it to the other side. We're resumed. Let's do it. So now that you have seen how to set up the cases, we're going to go ahead and tackle this question. Who's brave enough to work ahead of me? Has anybody worked ahead of me? You did? What'd you get?
I got 2 is less than and equal to negative x.
Yeah.
X is less than and equal to 6.
So, say it again.
2 is less than or and equal to x, and x is less than and equal to 6.
Like this?
Yes.
Okay. So the answers would be between 2 and 6. Anybody else work ahead? Jake, you did? What'd you get?
2, 6,
Same. Just could have sworn somebody said a negative number earlier today. Did you check your answers? We didn't check.
With what? Oh, no, I didn't check.
Well, let's see. Pick a number between 2 and 6.
3.
3. Okay. Let's see if it works. 3 minus 4 is -1, but the absolute value of -1 is +1. Is +1 greater than or equal to -2? Sure is. Woot. So it would appear as though all the other numbers fail, the ones that are outside, right? Like the number 0, which is to the left. I mean, because 0 minus 4 is -4, and the absolute value of -4 is +4. +4 is, oh. Huh. It would appear as though numbers outside of this zone also work. I wonder why. What about absolute value? Right, so what's your point?
I didn't set it up like that. I kind of just got like 2 numbers.
Well, you had to have inequalities.
Yeah, I like had x's.
Yeah.
Yeah.
Okay. But anyway, what kind of numbers are going to be on this left side? What kind of numbers will be the result of the left side? Positive numbers, right? Or the number 0. Last time I checked, all positive numbers and the number 0 happen to be greater than or equal to -2. This is what this says. Positive numbers that are greater than or equal to -2. That's always true. It's always true. So the answer for this one is all real numbers. But why? It's because I set it greater than or equal to a negative number. I mean, what if I had set it less than or equal to a negative number? What's up with that one? If I say absolute value of some things is less than or equal to a negative number.
It can't be less than a negative number.
Can't be less than a negative number, so no solutions. I could say the same thing like this. Absolute value of stuff less than 0, again, no solutions. I could say absolute value of some stuff equal to negative numbers, no solutions. None of those things are possible. So what kind of things are going to be all real numbers is the question. Well, absolute value of some stuff being greater than or equal to 0. Absolute value of some stuff being, well, I can't say strictly greater than 0 because sometimes equal to 0. So if I say strictly greater, that's not possible. But I could say greater than negative numbers. And what's that? Yeah, it can be equal to 0. But if I said strictly greater than 0, that doesn't guarantee that that works. But these are all real numbers, and these are all real numbers. Oh, I guess I could say greater than or equal to negative numbers. which is the example we just saw. So all three of these are no solutions, while all three of these are all real numbers. I don't need you to memorize those. I just need you to think about the questions before we get started. Because it's not that we had bad math skills. Your algebra was perfect. It's that you started before you thought about what the absolute value of the left side means. I'm just trying to train you guys to always be thinking before you start working. I want to change this question. It did say greater than, didn't it? Before I scribbled it out? No, I can't see it. There. I just wanted to switch the inequality over, just so I have a representation of every answer set possibility in my notes. This is not a trick question or anything like that. We just set up our two cases and go to town after we isolate the absolute value bars. So you divide by -2. What do you remember to do? Switch to a greater than symbol. So absolute x minus 1 is now greater than 3. We just set up our two cases now. We get x minus 1 being greater than 3, or the negative version of that. I'll use orange and blue because go Gators. Like that. Let's add 1. Easy peasy. X is greater than 4. Distribute your -1 and solve for x. One last time, remembering to flip the inequality over. And we're supposed to graph these things. I mean, for this one, if you wanted to graph this solution, you just draw a number line and shade the whole stinking thing. But these, numbers that are bigger than 4 or numbers that are less than -2, you see, they don't overlap. So on a number line, you got a situation like this going on. So we'd have to write that answer set as a union. From -infinity up to -2, union, 4 to infinity, like that. Ta-da! Cool beans? Not bad, right? I just wanted to make sure that you saw what happens if the answers didn't overlap. And that's why I switched the inequality over. Now the last two examples are just there just to be more challenging, but they're not different. They're just more challenging because there's more stuff going on. I was just trying to make them more. But it's done the same way. Nothing crazy here. Let's isolate. Divide by -2 on both sides. Luckily, these are both even numbers, so I can divide, and I'm going to get something pretty at least. Gets me absolute value of 2x plus 6, less than or equal, look what I did. I said greater than or equal to, that's what I said, greater than or equal to, -2x plus 6. And you just set up your two cases. I feel like this stuff is pretty straightforward. Hardest part about it is you have to solve two questions for each one and then check your answers. Best case scenario, 2x plus 6 was already positive, so greater than or equal to -2x plus 6. And worst case scenario, the 2x plus 6 was actually a negative number. green? There we go. All right. Let me get all my x's to one side, and I'd like them to be positive, so I'm just going to go ahead and add 2x to both sides. Give me 4x plus 6 greater than or equal to 6. Oh, subtract 6. Gives you 4x is greater than or equal to 0, and divide by 4. Oh, look at this. X is greater than or equal to 0. That says if you can use any positive number you want, or even the number 0, and you're in good shape. Yes?
How does negative 2x plus 2x equals 4 when they equal 0?
I added 2x over here. So I added the 2x to both sides. So it canceled on this side.
Oh.
Yeah, that did give me a 0. But over here I had to add them together. No, he's not wrong. Just all right, let's try this side. Just distribute that -1 and see what we have. Negative 2x minus 6 greater than or equal to negative 2x plus 6. Again, I'm going to add 2x to both sides because I don't have to goof around with negative x's if I can avoid it. And they're going to cancel here, and they're going to cancel here. Gives me negative 6 is greater than or equal to positive 6. Is that a true statement? No, it's definitely not. This is all kinds of wrong. It makes no sense. So then that's our only answer set. There it is. We're supposed to draw it on an underlining graphic, so that's what I included in the notes directions because I had some students that were still struggling with interval notation. So I figured, you know what, it wouldn't hurt to throw the graphs on there. That answer set says bracket 0 up to positive infinity, parentheses. Cool beans. Let's tackle this next one. I have time to finish it. You'll be the only class that's actually seen it. Congratulations. Everybody else can watch it. Let's isolate these absolute value bars. Ready? First, I want to add 2 to both sides. Three absolute x plus 1 absolute over 5 less than x plus 3. Where would you go from here? How would you handle it from here? Yeah, multiply both sides by 5. Where is my pink pen? I just realized my pink pen is missing. Scary. On the left side, I'll be left with 3 absolute x plus 1. And on the right side, I'll have 5x plus 15. Ew! There's got to be fraction answers. Yeah. There's not really a way to avoid it, unfortunately. So let's just go ahead and bite the bullet, divide both sides by 3. Gives us absolute x plus 1 is less than, 5/3 x plus 5. Big old meanie that I am, right? Fractions. So why is this question here? Just to make you work with fractions. That's really why. He gives me thumbs down. He gives me thumbs down. All right, anyway, now we can set up our positive and negative case. Positive case, pretend there was no bars. Negative case, there's bars, because, or there's parentheses because the x plus 1 was actually a negative number. I just did that color. You know that this x, you could think of it as 1x, right? You know what's a really convenient denominator for that 1 to have? A 3. I'm going to call it 3 over 3x because that is 1x. So when I subtract my 3 over 3x from both sides, What that gives me is 1 is less than 2 over 3x plus 5. Subtract your 5. I forgot to draw my little equal signs. Negative 4 is less than 2/3 x. And you've already seen this trick today. How am I going to make that 2 over 3 go away? Multiply by the reciprocal 3 over 2. On the right side, the 2/3 and 3/2 cancel each other, just leaving me an x. I have x is bigger than some negative number. Let's check it out. 4 times 3 is 12. 12 divided by 2 is 6. It says x is greater than negative 6. Yes.
In general, isn't the reciprocal going to be a negative also?
The reciprocal? No, that's the opposite reciprocal. That's for perpendicular lines is what you're remembering. They have opposite reciprocal slopes. All right, this one. We'll see how far we can get. Negative x minus 1. Oh, I forgot to write my x here. Thanks, too. Same trick. Instead of calling it negative x, I'm going to call it negative 1x, which even better would be negative 3 over 3x. It's negative 3 over 3x, so I can add this 3 over 3x, and oh, look how nice that's going to be. 5/3 plus 3/3, that's a whole number. That gives me negative 1 is less than, let's see, 5/3 and 3/3, that's 8. Oh, that's not a whole number. Darn it. It's 8/3. I thought I was going to get 9. Man. I have really worked myself into a tiny corner down here. Do you see this? How am I going to do this? If I subtract 5, it's going to give me negative 6. I am just out of space, folks. I'm out of space. I have to multiply both sides by 3 over 8. Well, that's 18 over 8, 9 over 2. Interesting. It's almost like nobody's listening to what I'm saying, but something very interesting just happened. Well, no, it gave me x is greater than negative 9 over 2. These both say x is greater than a negative number. That is just weird, isn't it? I feel like since everybody's ignoring me, I'll just leave it there and hope it doesn't show up on a test.